So the first thing we do is we need to find out what the derivative of our function is. Because we need to know where does the derivative equal 0. Because 0 is where it's going to change from increasing to decreasing or decreasing to increasing. So we set that equation then equal to 0. And we solve it. Now in this case, a great way to do that is to subtract the 1 from both sides and then divide by the 2. We then have negative 1/2 equals cosine of x. So we're just figuring out where does cosine equal negative 1/2. Yes, you should know your unit circles still. Yeah, I know. Weird, right? Now, a great way to do unit circle stuff is you can actually picture the circle there. And if it's negative 1/2, then that means it's like right along here. So the triangles that we're dealing with are going to be that and that. Looks like 120 degrees. Although we probably want to be in radians here. I've been doing degrees in all my other classes recently. What is that in radians?
3 pi over 4.
No. It is 2 pi over 3 for the top one.
Isn't it?
And the bottom one is 4 pi over 3.
Yeah, okay, that's what I was.
So, x equals 2 pi over 3 and 4 pi over 3. Now that we know what x is that makes it equal 0, we still have to figure out the intervals. So there's 3 candidate intervals right now. We have negative infinity up to, actually no, not negative infinity. Why not?
Oh, outside of the interval.
Yeah, because we're actually given an interval in this case. So we're going to go from 0 to 2 pi over 3. Then we have another interval from 2 pi over 3 up to 4 pi over 3. And then we have our interval that goes 4 pi over 3 out to 2 pi. So we need to know for each of those,
May God bless you.
is the derivative positive or negative within each of those? So pick a number that's inside each interval and plug it into the derivative function. Because I'm looking to see whether the derivative is positive or negative to know increasing or decreasing. All right, so when you test a number in each of those intervals, you should find that our first interval has a positive slope throughout it. Therefore, it is increasing over that interval. In our second interval, we got negative numbers in there, so that means it is decreasing. And then the last one, it was positive, therefore that one is increasing. And so those are our intervals where it's increasing or decreasing. Yes, technically when we wrote the increasing one out, we would write our interval union the other interval there. All right, now finally, for our local maximum minimum values, remember this is how we can check it using the intervals we found here, because we look to see where does it change from positive to negative or negative to positive. Now, of course, there's 2 different numbers where that happens, right? It changes at 2 pi over 3, and it changes at 4 pi over 3. All right, now at 2 pi over 3 up here, you notice that it changes from increasing to decreasing. Does that mean that it is a local maximum or a local minimum?
Max.
And I'm hearing a couple different things, and if you're ever not sure, envision it. So it is increasing and then it changes to decreasing. Notice that means it topped out. So that means that is a local max. The other one goes from decreasing to increasing, so that is a local minimum. Now, the thing about this process, though, is it's a little bit of a pain having to work with all these intervals. If I just wanted to go straight to finding out where the local maximum and minimum values were, I don't really want to have to go through the process here of first finding the zeros and then creating intervals for each of them and then figuring out whether the intervals are positive or negative. We should be able to streamline that some. And so that's going to be our goal today, is to streamline that process.
We're going to have to use the second derivative.
So from yesterday's notes, we have all this stuff up here in blue. That's the stuff we just used to answer that question. But now, what can we use about the first derivative and the second derivative in order to know where C would be a local maximum or a local minimum? Remember this graph here, this is the graph of f prime of x here. So, we know what's true about the first derivative, right? Remember, we knew that it happened where the first derivative was 0. But What is true about the second derivative for it to be a local, let's focus on the local maximum first. What's true about the second derivative in order for us to know that it is a local maximum? Well, this graph here is already the derivative, right? So the second derivative would be the slope of this graph. What is true about the slope at all of our local maximums? Remember, that's where it's changing from positive to negative. So for instance, this one's a local maximum.
0. 0.
What is true about the slope of my derivative function there?
What?
That slope, notice here at our local maximum, is negative. Here is also where it was a local maximum. You notice our slope there is negative. And here, it was a local minimum. Notice the slope of my derivative function here is positive. And so if we just want to know where is the local maximum and where is the local minimum, we then don't have to set up the intervals and test a bunch of numbers. We can go ahead and just find the first derivative and the second derivative. And so yes, into your notes now you got the second derivative test. All right, as you're getting this into your notes, notice the connection here. Of course, we're looking to see where the derivative of the function is 0. That's critical. That's the start for both of them. But when I'm going to be finding my minimum, notice what's true about the second derivative. The second derivative is positive. This might seem counterintuitive at first. So make sure that you're making yourself specially aware of that a positive second derivative actually means it's a minimum. The reason is because when we're looking at a minimum, notice it's increasing. It's increasing at an increasing rate when it is increasing. And so we're even going to delve into this a little bit more tomorrow when we look at concavity. But the whole idea is that we're changing to where it's increasing. It's accelerating if we think about it velocity and position. Versus if my second derivative is less than 0, that means that it's doing one of these. That's why it's the maximum. All right? Now to practice this idea, here's a big old table full of a whole bunch of numbers, right? We need to know, what are we looking for in order to find the local extrema? Remember, extrema just means the extremes, maximum, minimum. So in the notes that we just took, both the local maximum and the local minimum happen at the same place, right? The first thing we look for is, where does the derivative equal 0? So what I'm looking for here is I'm looking to see, where does the derivative function equal 0? So I start by narrowing my focus there. Now all I care about is those 3. Now I need to decide between those 3, which one's a local maximum, which one's local minimum. Now, for it to be a local maximum like this, what do I look for? Yep, we're looking for a negative second derivative. So we're looking to see where f double prime is a negative number. That means it's going to be a local maximum. So we have a local maximum here at x equals negative 2 and 6. Yep. That means we have a local minimum at x equals 1. And so the basic idea here is we figure out, where does the derivative equal 0? And then at each of those values, so that was here, here, and here, we have to figure out whether the second derivative is positive or negative. And so when doing one of these, like from an equation, you'd first figure out what is the derivative equation, set it equal to 0, and solve it. Once you have those solutions, then also find the second derivative and plug those solutions, those x values, into the second derivative. And that will tell you what your x values are for your actual solutions. And now I, of course, want to practice that idea. So here is an equation. We're going to go ahead and see how we apply it to an actual equation. So we got our original function. we know we're going to need the derivative and the second derivative. Some people like to find the first derivative and solve it and then do second derivative. I like to actually just knock out all my derivatives at once. So I'm just going to find f prime of x and then f double prime of x from there. So here's our derivative and our second derivative then.
Forgot about the drop.
Now that we know those, I now need to figure out, in order to use the second derivative test, first of all, where does f prime of x equal 0?
Yep.
So, we set 0 equal to the negative 6x squared plus 6x that we found. Solve it through. And so, it's nicely factorable, so I went ahead and factored out a negative 6x. If you factored out a 6x, of course, it'd work the same way. You get the same solutions of 0 and 1. Now remember, that tells me that I will theoretically have a local maximum and a local minimum at those values. I just have to decide for each one, is it local max or min?
Yeah.
And we know that by now taking both of those numbers and plugging them into the second derivative function. So we're going to figure out, what does f double prime of 0 equal? And what does f double prime of 1 equal? And really all we care about is the sign of the resulting answer, but we're going to go ahead and figure out what the answer is so we can know it. So you should find that the second derivative at 0 is 6, and the second derivative at 1 is negative 6. Now that we know that, we now have enough information to be able to say where is the local maximum and where is the local minimum. Which of our numbers, remember I'm asking about x values then, at which x value is the local maximum? 1. Remember, a local maximum is where the second derivative is negative. Now, the other one was positive, therefore, that's a local minimum. And so those are our answers. We got a local maximum at 1, and we have a local minimum at 0. All right, we got the basic idea down, I think, now. So go ahead and work through this problem and start to finish, find the local maximum and local minimum values, please.